Alright, so this video here is the stats practice test. Made this in 2023. Alright, so we're going to be putting all this data right here into our calculator. So we're going to go stat edit, alright, and put this in our list. When you put this in your list, you're going to get a box from this here that looks like such. Notice that there's no outliers. When I've done the y equals here, I chose the one with a dot so that if there were outliers, we'd see them, but there are none here. If you hit trace, you're going to be able to find these values here. All right, so let's go ahead and look at some of this. Do this, the min x here is 2, the Q1 is 3, the median, which is 5, the Q3, that's the 75th percentile, is 9, and then the max x is 15. So we're going to make this scale here. I'm going to go back and draw this, but you're going to go ahead and make a scale where it starts at, you can make it 0 to say 16, that works, and then you could just split it down, or you could count by ones, whatever, to make that scale. So I'm going to just put that, transfer that graph here. Remember that a graph without labels is a bunch of garbage, so you got to make sure you put that in there. So this is number of hours on the phone, and you could just put hours, on phone. That's fine. I don't have a better label than that, and then same thing would go up on top. So you're just going to transfer this onto here. Okay. The 3 measures of central tendency. Considering this is a normal data, the mode is not a measure of a center here, but we'll still go ahead and give that. So X bar, which you did in the 1var stats, is 6.05, and the mode was, and we can sort our data, and the mode is 2. Again, since it's not normal, it's not really the center, but that's okay. And median is 5. Okay, so a little better, is 5. All right, so in the standard deviation on this one, that's the one that it's this squiggly. There's 2 of them in there. So in your 1var stats, it looks like that, but that little squiggly, that sigma is 3.76. The smaller this number is, the more compact the data, and so we can compare data sets. But in this, it's just 3.76. Now, what are the extremes for an outlier? Since this is not normal data, we're going to use the 1.5 rule. So we're going to get that magic number, again, that's just been made up. That's what stats often are, just to organize our data. So Q3 was 9, I believe, and was 9, and Q1 was 3. So I got 9 minus 3, and then multiply by 1.5. So this magic number is 9 here. That is not the sole thing. But then you take Q3 plus this magic number, and that in this case is 18, because Q3 was 9. So it has to be above 18 in order to be an outlier. So 18 is not an outlier. And then Q1 minus this magic number. So in this case, Q1 is 3, so -6, which is impossible. So there's definitely, and it's got to be below -6. So there's no outliers below. Impossible, because we're talking about hours on phone. But still, you're going to use the 1.5 rule when we have non-normal data to figure out outliers. When we use this for the entirety of the school, or for Algebra B, sorry, is because you guys are older. If this was based upon your guys' class, then you guys are older than the Algebra B students, so you maybe freshmen, not everyone's going to have a cell phone, so you're going to have some people that are going to have zeros, that kind of stuff, or they might have a more restricted phone use still as a freshman compared to, say, sophomores and juniors and seniors. So that's why you wouldn't want to compare it to that. It's not the same population type. Oops. And now make a histogram. So again, we're going to sort this data, and we're going to choose this. So we're going to make 5 bars here on our own. So we went from 2 to 15, I think it is, 2 to 15. So 2 to 15. So if I did 15 minus 2, that's 13, and I divide by 5 because I want 5 bars, then that's like 2.6. So if I use 2.6, that would be a good width. However, I want to use, I'm going to go up from this. I'm going to go to to 3 for my width here. So that's my width. So that's how I'm going to do that. Upper number minus lower number and divide by 5 because we don't have 5 bars. If I want 6 bars, I do 6. So I'll start at 2, and then it goes to 5, 8, 11, 14, and 17. Now recall that 5 goes this way, 8 goes this way. So you're going to count those. These are dividing markers. We're going to count how many numbers are between 2 and 5, 5 and 8, etc. Remember that, again, this is garbage if you do not have labels. So this is hours on cell phone and on cell. So take the time to actually write that out. Number of people is going to go on this side. And then the top would be like Mr. Walters, whatever hour you are. Okay. Now, again, you want to sort the data here. So I'm going to go to sort in my list. So you go stat, edit, sort. 10 numbers that fall between 2 and 4. So 2 and 4, there's 10 numbers. So count that up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think that's 10. So I'm going to make my bar up to 2 to 4. That's 10. And then I'm going to count from 5 to 8. So again, 5 was not included in this first bar because it goes to the right of it. It goes up to 5, but not 5. So if I count the number, so 5, 6, and 7s. So that's 2, 4, 6 numbers. So up to 6. That looks like 6. 6. Okay. And then from 8 to 11, there's no 8s, but there's 9s and 10s. There's 3 of those. And then 11 to 14, there's just 1. And 14 and 15, there's 2. And that's what you're looking at here. Again, title, the top. This question a second time. I didn't realize I'd already asked this up in the beginning part, but for the classes data world ledgers, and we just did that already. That was the numbers that we had back here, 18 and up and below 6. All right, so filling out this normal bell curve here. We're using the empirical rule, 68, 95, 99.7. So it's always going to be, so these runs in red are going to be always the same. So it's 50th percentile in the middle. And half of 68, if I divide that, that's 34. So I'm going to add 34 to 50, so it's 84. Add, and then subtract it, so it's 16. Then I do half of 95, which is 47.5. So I'm going to change colors here. And that's 97.5. So the ones that are in orange, that's 2 standard deviations away. So 95% of the population's there. And then let's do another color. Let's go blue. And 99.7 divided by 2 is 49.85. So that's 99.85 and 0.15. Okay? And so now those numbers which are there will never change. Now the numbers that are with this, there's going to be some more data here. R is 8.2. And the standard deviation was 0.9. Okay, so 8.2. And then I'm going to just keep on adding 0.9 up. So this is 9.1, 10, 10.9. Go the other direction, 7.3, 8.4, oops, 6.4, sorry, 6.4, and 5.5. Okay, so that's great. Z-score for my mom, who's got a shoe size of 7. I really don't know what her shoe size is, but Z-score, you just find how many standard deviations away. So it's x minus x bar, or standard deviation. So 7 minus 8.2 over 0.9. So make sure you do that. If you're typing that all in once, these are going to be in parentheses, or you can do 7 minus 8.2, hit enter, then divide by 0.9. So her Z-score is negative 1.33. So she's not one of these perfect numbers. She's not in this list here. So we have to use a Z-score. So what percentile is she? Then we go to the normal CDF. And so depends how you're using your calculator, but your calculator might already have the number in there, but negative 10,000, negative 1.33, use 2 decimal places there. 0, 1. A lot of the calculators actually automatically assume 0 and 1, which is fine. Type it in. So she is at 0.0917, so 9.17%. So she is a shoe size is the same size or bigger than 9.17% of the population on that. So conversely, if she has a smaller shoe size than 90.83, yeah, 90.83, doing that mental math. All right, what are the extremes for outliers? So shoe sizes that are less than 5.5, so it's a 3 standard deviation rule, or X is greater than 10.9. Again, this is just made up data, so I don't think a shoe size of 11 would really be an outlier, but according to this, it is. So it's got to be less than the third standard deviation or greater than the third standard deviation, not equal to. 5.5 is not, 10.9 is not. What percent of the population has greater than a 9.1 shoe size? Now, this one falls on the curve, so we're going to use that. So we don't need to use the normal CDF in this case because it's on the curve. So 84% have less of the same shoe size or less, so therefore it is 100 minus 84 in this case because we want the other side. So 16% is our answer. What probability the person selected would be within 3 standard deviations of the mean? That's just asking about the 99.7, the empirical rule. 95% of the population, which would fall between which 2 shoe sizes. So you go back to the chart here. 2 standard deviations, 95% is 2 standard deviations, so the ones in orange. So 6.4 and 10. 6.4 and 10. And number 9 has nothing to do with that one, but number 9, skewed left means the outliers are to the left, like that. So the big thing in this is that the average gets pulled. The average is pulled towards the outliers. So so you got these outliers that are out here. They're stretching the data out like this, and the average is there, but the median is still there in the peak. Okay. Number 10, 10, and 11 here, 2 tens. These are generic questions. So we're looking at 1 standard deviation below, and so that's the 16th percentile. And so we're looking for when it's less than that, so 16th percentile. So 16% is our answer there. 2 standard deviations up. So if you look at the normal curve, here's the middle. It's this one right here, which is 97.5. So 97.5. So because it's less than, we want that direction, so it's 97.5. If I had greater than, it'd be 2.5 if that was asking it. In this case, it is the third question here. It is asking for the greater one, but it is the same if it was greater than or less than. All right, moving on. Use the data and the answer to the following questions: percent homework versus test percent. So when you put this in the calculator, you get the stats and you do linear regression, so stat calc on that, and you get A is 0.47, B is 43.57, and the correlation coefficient is 0.75. So the equation is y equals 0.47 because it's linear. It shows that this is our equation, ax plus b. So a goes in front of the x, b is the constant, plus 43.57. Correlation coefficient, that's the r. See me if you don't have that showing up. You need to have that showing up before the test. So what does this correlation coefficient tell us about this? So this is moderately strong. So 0.8 is the cutoff line. Remember, it goes from -1 to 1. And so from 0.8 on up is really strong. -0.8 and down, these are strong. And then like from 0.5 to 0.8, these are moderately strong. So we have there's a pretty good relationship between your homework percent and your test percent. So this is saying that, what is this correlation coefficient? There's a moderately strong strong linear relationship. We're doing linear. And I want a little bit more there. But moderately strong, and then I would say that because it's a direct relationship, as homework percent goes up, we more likely, there's a relationship as homework percent goes up, so does test percent. And of course, it's not perfect because there's some people that are ones that are just honestly lazy about their homework and they do really well on their tests. It's usually 1 or 2 kids in a class. And then there's others that do well on their homework but struggle on their tests. 70%, I'm going to put 70% in there. So I'm just going to literally type that in. So 0.47 times 70 and plus the 43.5. Now, I'm actually using 70 there because notice these are in actual there. So 76.4. So if you're getting 70% in your homework, you get about a 76.4 in your test. So it's pretty strong relationship actually in your guys. All right, the difference between parameter and statistic parameter. Parameter, so like when we say like X bar, instead of saying X bar, we actually use that mu. Parameter, so it's sort of bad writing, mu. That means the population. It's very easy to remember because the P's. But so essentially, our data is for everybody. That's when you talk about that. So it's a different scenario. Where statistic, where you have a sampling, right? You random sample or have some sort of a survey. So statistic, that's your X bar, and that's for a sample. It's not for the entire population. So that's a big difference there. All right, moving on. All right, so factoring this, we're looking at 2 numbers. So this is a simple factor because it's a 1 in front there. So 2 numbers multiplied to be -15, add to be -2. And so -5 and 3 this is a selection there. Now number 15 is a harder one. So remember I'm going to do this up top here. So 6x squared plus 7x plus 2. The answer is obviously down there. I need these things to FOIL out to be the original equation. And so the shortcut trick here is 12 multiply A and C. So we're going to group this. So 6x squared. Need 2 numbers that multiply to be 12 and add to be 7. So 4 times 3. So 4x plus 3x plus 2. And now you group it. There, I can pull out of the 6x squared plus 4x. I can pull a 2x. So that gives me 3x plus 2. So again, pulling out, it means I'm going to divide in that. 3x plus 2, there's nothing in common. So I'm going to pull out just a 1. And magically, look at that. It's 3x plus 2, 3x plus 2. I'm going to pull those 2 out to become 3x plus 2 and 2x plus 1. And the reason why we spend so much time on this factoring, it's going to be important in data B and for one of the units that you need to be able to factor. All right, solving. Recognize the type of equation that you have here. So this is a quadratic. So it's equal to 3 right now. So I'm going to make this equal to 0. So by subtracting that across. And I did the quadratic formula here. So when I do the quadratic, so formula, A to B, and that's up on the board here still. And b squared minus 4ac all over 2a. So a is the number in front of x squared. That's a, that's b, that's c. And so that's what I'm doing. I'm putting this in. So when I do what's underneath the radical here, it's b squared, so 49 minus 4 times a times c. And so that's how you got the 24. And so you get these 2 decimals. Now, I didn't tell you that you had to solve this one algebraically, but the other way you could have done this is you could have graphed it. 2x squared plus 7x equals 3. And if you do the graph, it looks something like this. And you see when they cross, and those are when you do the second calculate intersect, that's what you get. Solving this one analytically, also same thing, I could have done this graphically, but I'm going to ask you to solve it analytically on the test. Got to isolate. There's only 1 log, so we're going to isolate the log. So I'm going to add 2 across and divide by 4. So that's going to give me, if I add 2 across, that's going to be 12 on the other side, and divide by 4, so that makes it 3. And then now once you get a log by itself, you rewrite it as in its exponential form. So 2 cubed equals x plus 1. So 8 equals x plus 1. So that's how we get 7. Just like the last one, isolate. So isolate e to the x. So I'm going to add 3 divided by 4. So that's 20 divided by 4, which is 5. And once you get that e by itself, you take the natural log of both sides. And the beautiful thing, so that comes down. Beautiful thing about e and natural log is they're inverses of each other, so they cancel each other out. And so that's why I have natural log of 5. Graphing here. So this graph has been, so recognize that it's a quadratic. So for crying out loud, you got to know that it's a parabola. It's either opening up or opening down. The fact this is a positive, it's opening up. So the locator point, it's been shifted right 4 and up 3. So it's the locator point is 4, 3. And it's opening up, go up 2 on each side. And whew, there's your graph. Now your domain for quadratics, it's everything. Your lowest number comes first. And then the range, so the lowest number here is 4. Or not 4, 3. So 3, it's inclusive at 3. It goes down and touches 3. So there's your domain range. Now the next one here is an exponential. All right, so first off, this is a calculator allowed one, so you should be able to at least have an idea. But it's an exponential, so it needs to look like an exponential. So it looks like this, or it looks like this. The fact that it's base 2 means it's this one here. So we're looking for the locator point. So it's at -4. Exponentials and logs are the tricky ones. So it's -4, -2. So -4, -2. It's shifted down. The graph is shifted down. So -5 is your horizontal asymptote. So exponentials have that horizontal asymptote. So draw the line, and then I just draw. So it's a growth one. Boom. That's the quick graph here. Domain, it's everything for exponentials. In the range, it is not going to get down to -5. It'll come close, but it will not touch -5. So it's a parenthesis with -5. Last one, log one. So we have a base. It's either going to be like this, or it's going to be like this. But we've got to get ourselves a vertical asymptote, and that vertical asymptote is at 5. So 1, 2, 3, 4, 5, because that's what makes the inside equal to 0. So there's your 5. And so then you also do so set it equal to 0 for the vertical asymptote, and then you do it equal to 1, because that's what's about logs. It's what makes them tricky. So if you do that, you get 6 comma, I shouldn't have used 1, but I did. There's a 1 here, so 6 comma 1. And there's no reflection. So there you go. My domain, it goes all the way to this vertical asymptote, but does not touch it. So therefore, my domain is 5 to infinity. My range is everything. There you go. Okay.